Airbags save lives by reducing the forces exerted on the driver and passengers in an automobile collision. Cars are designed with a crumple zone in the front of the car, and in the event of an impact, the passenger compartment decelerates over a distance about 1 meter. An occupant restrained by seatbelts and airbags decelerates in the distance of only about 5 millimeters. So some of the pertinent like concepts that are going to be related to this problem are especially Newton's first law, which basically states that an object in constant motion or at rest, if no force is acted upon it, they're going to stay in motion or at rest. And so the way that this relates to this problem is, for example, if a car is going 60 miles per hour and really rapidly decelerates, the person is still going to be going at that 60 miles per hour, because really the only forces acting on them are the forces of gravity and the normal force and maybe a tiny bit of friction from the seat. And this is in the case if a person isn't wearing a seatbelt. So if that car really rapidly decelerates, the person's just going to keep going 60 miles per hour until they hit the dashboard or windshield or something like that. So yeah, their inertia is going to keep them continuing forward. So part A is asking about a 60 kilogram person that's traveling at 50 meters per second, and it's asking about the net force on the person if they're wearing a seatbelt and if the airbag deploys in a head-on collision. So my free body diagram for this, since this is an estimate, I just made the net force that force of the seatbelt and airbag, and that's going to be in the negative I-hat direction, that force. There probably is going to be some other forces on the driver, like the force of the seat, like the friction of the seat on the person. But since this is just an estimate, we can just look at the net force as being the force of the seatbelt and the airbag. So our notes for this situation are just that the distance of deceleration is going to be 1 meter, and then the mass of the passenger, and then the velocities. So with this information, we can use our kinematics equations to solve for acceleration. And then once we solve for acceleration, we can use Newton's second law, F equals ma, in order to solve for the net force. So first thing I did was just solve for that acceleration, which I just used one of the kinematics equations and derived for A, and an A came out as negative 112.5 meters per second squared. Now we can solve for the force. So the net force is just going to be the mass times the acceleration, and so the net force here comes out being negative 6,750 newtons. So that's the answer for part A. That's going to be the net force acting on that person in this collision. So part B is asking about the person if they're not restrained by a seatbelt or airbag. So the only difference here is that distance of deceleration is going to be 5 millimeters rather than 1 meter. You can see the free body diagram is actually more or less identical to part A. So we're going to be able to use the exact same process as part A, just with a different distance. So go ahead and getting started on that. We can solve for acceleration and find out that in this case it's going to be negative 22,500 meters per second squared. And then plugging that into the force equation, the net force comes out being 1.35 times 10 to the 6 newtons. So this number is a lot bigger than part A. It's actually 200 times more force. So yeah, it's definitely good to wear your seatbelt, I'd say. So that's all I have for this problem. Thanks for watching.